So now I want to start with a big topic, derivatives for functions of several variables. And I want to start there by, as we often do, sort of taking a look back to see how that helps us go forward. So I want to start with a review for derivatives for good old y equals f of x. So you could think of that as a rate which represents a change in y over the change in x. Now, if you think about a simple y equals f of x function, it's just a linear function. The graph is straight, and therefore it's easy to calculate the rate of change, which is the derivative. Now, for nonlinear functions, you could represent the derivative graphically by taking the graph of the function and zooming in on a point of the AB of the graph to reveal a straight line. That line is called the tangent line, and the slope of that line would be the derivative at that point. Numerically, you could estimate the derivative at that point by taking another nearby point and just calculating the slope using those 2 points. And then algebraically, you could define the derivative or the rate as a limit. But then to actually calculate it, you don't use limits, you use all these shortcuts that we know. So what do these different things actually look like? So here we have, the derivative of f of x, so f sub x, at a point x1 was approximately just taking 2 points, y2 minus y1 over x2 minus x1. So, for example, if we want to know the derivative at the x value 0.5, we could just take first the point where x equals 0.5, and then a nearby point from this table of values. Let's say where x equals 1 and y equals 1. So here are for our function y equals x squared. So we've got those 2 points, and then we just calculate delta y over delta x. And you get 1 minus 0.25 over 1 minus 0.5. Calculate that, and you get 1.5. And that's an approximate, and that's the rate between those 2 points. And we'd say that's approximately the rate at the point x equals 0.5. But graphically, you could do it in the following way. You could say, go down a bit. So graphically, you could say on the left, you've got the original function y equals x squared. And let's say, again, we're sitting in the rate at the point x equals 0.5. And if you zoom in on that point on the graph, that's what's depicted on the right side. And you can see that you're basically starting to get a straight line. And if you zoom in even further, you'll get more of a straight line. And visually, you can estimate the slope of that line is approximately 1. And now finally, to do it algebraically and precisely, we could define the limit, define the derivative using the limits by saying its limit as h goes to 0 of f of x plus h minus f of x over h. And then there's a way to calculate that for our function y equals x squared. We're not going to do that. We're just going to say we know what the rule is and what the shortcut tells us. So we actually have all these different rules for calculating the derivative. Derivative of 3x to the 7 is 21x to the 6. Derivative of sine x is cos x, etc., etc. And so therefore, for f of x equals x squared, the derivative of that is going to be 2x. And therefore, at the point where x equals 0.5, the derivative of that is 1. Let me take a moment to mention that for the derivative, I am using a notation that you may or may not have seen before. This is the notation that we will be using when we take derivatives. You may be more familiar with the prime notation. You should previously have seen the df dx notation. So we will not be using the prime notation in this course. There's a really, really good reason for that. That's coming up shortly. The reason is coming up shortly, and I want you to start getting used to this notation for the derivative, which is why I've started to use it already. Okay, so that was a review of derivatives for functions that you know about, y equals f of x. So now let's talk about an intro to partial derivatives. So if we have a function z equals f of xy, we're going to be able to understand derivative of this function in a similar way. So we're going to answer two questions. First of all, with a function of two variables or more, how does it make sense to talk about the derivative in 3 dimensions or later on in more dimensions? Second, once we believe that it is possible to have a derivative, how can we say what it is? So let's start with this example. Let's consider the plane, and we've seen planes before. So with the equation z equals 1 minus x plus 2y. So let's look at a numerical representation of this equation. So on the bottom, across the horizontal on the bottom, we've got x values 0, 1, 2, 3, and then vertically on the left, kind of like a vertical axis, we've got the y values 0, 1, 2, 3. Okay. So what could it mean to talk about the rate of change of this function? So some possibilities for this, we want to talk about how does the function change. In this case, we're taking z to be the function value. And if you'll recall, all these values in the interior, these are the function values. So looking at these values, what does it mean to talk about how those function values change? And it should be a rate with respect to something else. So two things we could talk about are one thing which we're used to, which is how does the value of the function change as x changes. But in addition, we've got another new thing we can talk about, which is how does the function change as y changes. So let's actually take a moment to talk about that. So let's pick a point to start at. So let's, for example, start at the point x equals 0, y equals 1. So from that point, how does the value of the function change as x changes? So x changes in, if you like, going in the rightward direction. And you can see that as x increases by 1, the value of the function goes down by 1. And then if you keep going, that's still true. X goes up by 1, the function goes down by 1. And again, x goes up by 1, function goes down by 1. So in fact, what we've got here is a very consistent, in fact, constant rate of change. So the way the function changes as x changes by 1, the function, or the z value, we could say it decreases by 1, but I'm just going to say it changes by -1. So we always have the positive or negative, we keep it with the number. Okay, now we can talk about similarly, how does the function value change as y changes? So again, starting from the same point. So starting from that point, as y increases by 1, well, the function increases by 2. And that keeps happening. As we go up another step, as y increases by 1, again, the function value increases by 2. And in fact, the rate of change for this particular function is constant everywhere. It doesn't matter where we start, starting from this point over here. As x increases by 1, the function decreases by 1. Over here, as y changes by 1, the z value changes by 2. So let's just fill that in for the y change. So as y changes by 1, z changes by 2. So for this for this particular function, we've actually got a nice way to talk about what the rate is. And that's from the numerical representation. Now let's look at a graphical representation. So we've got a plane, but this plane is tilted in space. So how are we going to talk about these rates? So here's a nice way to do it. So we're going to take this surface, which is a plane, and we're going to rotate it. We're going to rotate it so that we're only seeing it from the XZ perspective. So notice that the horizontal, so from this perspective, the horizontal, oops, sorry about that. Okay. So from this perspective, nope. All right, hold on one sec. So from this perspective, goodness. Little tech issue here, sorry about that. So from this perspective, the x-axis is on the horizontal axis, and the vertical axis is the z-axis. And if you notice, because we're looking at it from this perspective, the y-axis pretty much doesn't appear to us. Okay. So, having done that, so now we've got the red line, which represents a trace for y equals 2. And since y is constant on that red line, z is a function of x. So what is the slope of that line? And let's estimate visually. And we can estimate visually because the way I've presented this, 1 unit of x is about the same size as 1 unit of z. So that line, it looks like the slope is about -1. And I put a little key on the right side to use it to help make the comparison. Okay. So again, for our same function, there we go. Okay. So for our same function, now let's look at it from the YZ point of view. So notice that now on the horizontal axis, we've got Y values, and on the vertical axis, we've got Z values, and now we've rotated it so that really X values, we can't distinguish between them. So now the green line is the trace for X equals 3. Now, since X is constant, Z is a function of Y along that green trace line. So what is the slope of that line visually estimating? So using our little key, just to look back for a second, using our little key, it's certainly steeper than the line y equals, than a slope 1 line. So it's bigger than that, and we could approximate that the slope is 2. So the rate of change of z with respect to y here, we could say maybe it's about 2. And that's a visual estimation. So this is, this is one possible meaning for the derivative of z equals f of xy. So numerically, we can find the change in z over the change in x as y and constant, or vice versa, the change in z over the change in y with x being constant. Graphically, you can draw this a traced line, which in this case is a straight line, and the slope of that line is your derivative. So that's what a derivative could be. So what's the notation for this thing? So notation for derivatives. The derivative of the function f with x varying and other variables constant is most commonly written as this notation right here, df dx, but you'll notice that the d is curvy. So this is called the partial derivative of f with respect to x, and that curvy d indicates that there are other variables that are being held constant. There are a couple ways to pronounce this. The most common is just to say partial df dx, but sometimes we're in a rush, we'll just say df dx, and we'll know from the context that it's a partial derivative. So there are some other notations for this partial derivative. So first of all, if you're just talking about the function generally, we've got df dx, we've got d sub x of f dx. And so that indicates that you're taking the change in f with only x varying, and then in the bottom you've got relative to a change in x. Also, you can take the derivative on the outside, so you could say ddx or partial ddx of f. We've also got the notation which I showed you just before, which is f sub x. Then you've also got big D sub x of f. And then, of course, dz dx, where we use the z variable and the z value and the f function. We use them almost interchangeably. Okay, so some other notation. What if we want to talk about the derivative? We want to talk about the value at a specific point. So there are all these different notations. The easiest one to use, and probably the one I'm going to generally use, is this one, because it writes f sub x is basically written as a function. This is the one that kind of looks the most like the prime notation that you probably saw before. So f sub x, and then you just say of whatever point it is. And remember, of course, we're plugging in x and y values. So say of a comma b. Now you can use it with the df dx notation, but here it's a little complicated. In this case, you have to put the standard thing we do is you put brackets around the expression and then put a little ab in the corner as that indication. And then finally, the reason why we do not use prime notation. We can't use prime notation to indicate a derivative, since just marking prime does not indicate which input is varying. Before, with y equals f of x, there's only one input variable. So prime, there's no, it's completely clear, there's no ambiguity about which is the input variable varying. Now we have to specify. So no more prime notation. Okay, so now that we've got this notation, let's revisit the function that we had before, f of xy equals 1 minus x plus 2y. And now we can make these statements. So for that function, partial df dx equals, as we saw before, it's negative 1. And partial df dy, as we saw before, that value is 2. This one's pretty easy because the rates were constant. And there are a number of ways, when the rate is constant, a number of ways to see what the value is. Okay. So, and of course, when rate is constant, what we mean, another way to say that is that we've got a linear function. So let's take a moment to look at linear functions, both in the previous case, y equals f of x, and for our new case, z equals f of xy. So first of all, you've got the formula. Standard formula can be written y equals mx plus b, or in our multivariable case, z equals ax plus by plus c. What's the graph? For a single variable function, it looks like a line. For a function of two variables, z equals f of xy, it looks like a plane. And what is the derivative? If you've got the formula, what's the derivative? Well, y equals mx plus b, we know the derivative is just m, the coefficient of x. Now, if you've got z equals ax plus by plus c, what's the derivative going to be? Well, derivative with respect to x is going to be the coefficient of the x variable. Derivative with respect to y will be the coefficient of the y variable. So if you didn't recognize that from the previous example, we can take a moment to recognize that now. And then looking at the graph, what's the derivative? Well, for y equals f of x, it's the slope of the line. And for z equals f of xy, it's the slope of a trace. And as we saw before, each trace in this case is going to be a straight line. So that sort of handles the case when we've got a linear function. But as we know, of course, talking about rates when functions are linear is very straightforward. And in single variable calculus, you learn to talk about how can you talk about rates when a function is nonlinear. And we talked a little bit about that a couple minutes ago, and now we're going to extend that to talking about rates when z equals f of xy. So we can do this very similarly, numerically. So here's a function giving you a rather annoyingly complex formula. F of xy equals 4xy times e to the negative x squared minus y squared. And let's say we're at the point 1, 0.5, 0.57. So here's the numerical representation. And so we imagine that we are at x equals 1, y equals 0.5, and the z value is 0.57, puts us at that point right there. So what does it mean to talk about the rate at that point? Well, we can do what we did before. We can talk about the rate of change in the function value as x changes. And we can do that by, if you like, head on the table heading to the right. So since x is 1, a sort of easy thing would be to take x equals 2, but of course we know we're going to get a better approximation of the rate if we take the closest possible value that we can. So we'll use this other point. So at this other point, we know that the change in x over here is 0.5, and then the change in the function value, well, if you calculate it, it's negative 0.32. So just taking that negative, so the change in f, negative 0.32, divided by the change in x, which is 0.5, work it out, and you get negative 0.64. So there's your rate using those 2 points, and of course it's an approximation. But now, of course, we know that we can also talk about another rate, which is what is the rate as y changes and x is constant. And we could do that by heading in the vertical direction. So again, you could take y changing by 1, but we know we'll just get a better approximation if we take y changing by half. So in that case, we know that moving vertically, moving up, the change in y is going to be 0.5, and we get the change in the function is negative 0.03 using this point. And therefore, when we divide delta f over delta y, we just get negative 0.06. So that's how we can think about it numerically. Now, what about graphically? So graphically, let's look at a couple different graphs here. So first of all, on the left side here, we've got the function. Now, of course, the graph is curving and slopes are not constants. So let's hone in on the point where x equals 1 and y equals 0.5. So I've got the trace in green where x equals 1 and the trace in red where y equals 0.5, and they'll intersect at the point we're interested in. So notice that there's a small box on the graph containing that point. If you take that box and zoom in or blow it up, you'll see what's on the right side. And what you start to see as we've kind of zoomed in quite a bit is it starts to look like a plane. And of course, we know that we can talk about what rates are on a plane because all traces are straight lines. So one way we can do that graphically is by taking that and we're going to rotate it. So let's talk about the rate of change. So from the xz orientation, so what are changes in z relative to changes in x as y is constant? So let's rotate the graph to that perspective, and we will see the graph on the left. So let's make a visual approximation. What does the rate of change look like? Well, clearly it's negative, and it's going kind of downish. So, but it's not quite negative 1. So maybe it's like negative half. So let's say approximately negative a half. So, okay. Now what about on the right side? So on the right side, we've got z as a function of y. And we want to know what's the slope of that line. Well, okay. It's certainly positive. But but it's relatively flat. So it's certainly greater than 0 and less than 1. You might say positive a half, positive a third, something like that. So let's just make an approximation. We'll just say, okay, it's approximately 0.5. Okay. So notice, and I'll just mention that this is the way that I prefer to do it, but another possibility, in this case, we zoomed in to see a plane and then talked about the traces. Another possibility is to draw the traces and then say, well, now that we've got a trace and z is a function of x, imagine zooming in or imagine making the tangent line. That's an alternate way to do it. So of course, talking about the derivative numerically, talking about it graphically, these are all approximations. So now we're going to answer the question, how do we, given the formula, calculate a derivative exactly? And the key idea in this case, when we talk about derivative of the function with respect to x, we know that we talk about what the value of the function is changing as x is changing, and we want y to be constant. So when we calculate the derivative, we're going to use the same idea. So for this function, let's calculate the derivative, first df dx and then df dy. So what is going to be the derivative of this function with respect to x? Well, we've got 0.1 x squared plus 0.2 xy plus 0.05 y squared. Take the derivative of the first term, and you'll just get 0.2x. Take the derivative of the second term, and what happens? We treat y as a constant. So therefore, it's as if we have 0.2y as the constant coefficient and then an x. So the derivative of that will just be 0.2y. And then finally, 0.05y squared. Derivative with respect to x means y is a constant. That whole term we're treating as a constant. So the derivative will be 0. And there you go. Now we can do the exact same thing for the function with derivative with respect to y. So what is df dy in this case? So derivative of the first term, 0.1 x squared, since we're taking derivative with respect to y, we're treating x like a constant. Derivative of that term will be 0. So now 0.2 xy, derivative of that term with respect to y, we're treating x as a constant, 0.2x. And then in the third term, derivative of 0.05 y squared, you just get 0.1 y. So taking these partial derivatives is actually really straightforward with one key step. You must remember you're taking the derivative with respect to which variable, and therefore keep in mind that the other variable you treat as a constant. That's the key step. Okay, so I'm just going to mention in passing that in the same way that we defined derivatives initially using limits, we can also do the same thing with these multivariable derivatives as well. So for the derivative df dx, we want to take the limit as h goes to 0. Now where is that h going to appear? Remember that with df dx we want y to stay constant. Therefore, the limit as h goes to 0, f of x plus h comma y minus f of xy. So notice that the plus h, all over h. Notice that the plus h is only in the first coordinate and the y is constant.